Sophie Le-Bourva, who is an associate director, structural engineer and associate director at Arab. She studied civil engineering and architecture in France at the École Polytechnique, the École Nationale des Ponts et Chaussées, and the École d'Architecture Paris-Le Seine. She graduated from the Transdisciplinary Design for the Built Environment Master's course in Cambridge. And Sophie has a wide experience of design, management, and construction of high-profile projects in Europe involving complex metal structures, non-linear structures, and non-regular geometries and damping techniques. She's currently a member of the École Nationale des Ponts et Chaussées Scientific Council, and she has regularly been involved in teaching and lecturing in various architecture schools in Europe and North America. And over the years, she's built particularly strong links with the AA here, and she currently sits on the council at the AA. Her expertise, or her educational background, and her professional experience of design-led projects has given her a particular interest in the architectural perception of structures, the interaction of design disciplines, and the actual making of building components. So please welcome for me Sophie Le-Bourva.
Well, I knew following Wolf would be quite hard work, but I didn't realize it would be that bad. But luckily, there's one thing that we've done is that we have split materials between each other. So he's essentially talked to you about steel structures, and it's fair to be said that actually steel structures have been slightly more advanced in this field than many of the other materials. So actually, by pure and sheer luck, I'm talking about other materials than Wolf, but I won't get as much in the sort of bigger issues of sort of organizations that he has extremely aptly sort of described. But we have exactly the same sort of questions, exactly the same sort of issues. We use the same sort of set of tools, mix them with all the issues of mixing them. We have to adapt to various countries, various places, various abilities, both at architect level and at contractor levels or fabricator levels. So we have very, very similar sort of questions that are being asked from us. And really the sort of transition to digital is probably the thing that is marking our generation. It's fantastic. I arrived at Arab and they were still drawing by pencil with drawing tables. That's okay. I'm slightly ancient now, but I'm not that ancient either. So in sort of 20 years, we've gone from drawing on drawing tables into actually full digital 3D modeling, BIM models, sort of transfer of data in 3D instead of actually even 2D models in half of the cases. So a total transition, both in our industry, our consultant groups, but also in all the fabricators, or at least not all of them, but they are all striving to this. So what's happening is that suddenly there are new professions arriving, or new roles, let's say, which have to do with mathematics, programming, all these kind of little bits of translation from one software to another, all the sort of scripting, the parametrics. Suddenly there are mathematicians being hired by architect practices, but also by engineering practices. And the split as to who does what at the moment is still very fluid, as you've described. I think sometimes it's going to be the architect, sometimes it's going to be the engineer, sometimes it's going to be a third party, or it's even a combination of the three, as you will see on one or two of the examples. So I think a lot of things are sort of still moving around and being quite fluid. The thing that is happening also very clearly is that technological, the examples where this is stemming from, as you said, are often the sort of, the models, the tools are coming from the manufacturing industries of airplanes and actually often a lot of airplane things. So they have some effect on what we design. They've had some effects on the sort of type of building. This whole generation of weird shape and weird surfaces is largely coming from these tools. These tools were made to do those weird shapes for airplanes. And they've been borrowed and appropriated by architects and turned into their own tools, but I think the tools has an influence on what is actually happening in terms of design. And you may wish to sometimes challenge what the tool is doing in order to sort of retain or regain some of your sort of design freedom or your design abilities. But that doesn't mean they're mutually exclusive. Those tools are fantastic for more regular buildings too, and actually that's possibly where you capitalize most onto their benefits. And we're using those tools to do our most complicated projects very often, but actually we should be using them for all our projects, and that's certainly something we are striving for. Making is something which is currently very much in the air. There's a new course or new courses being created at The with Design and Make in Hook Park. There is a fantastic exhibition at the V&A called the Power of Making right now, which is going from crafts to sort of full digital prototyping methods and how the two can actually enrich each other. So it's something which is really very much of the time. And I thought I'd just show you a few photos of what making might mean for the construction industry. This is actually a set of fabrication photos of the Millennium Bridge in London. And you sort of see all the sort of range from the cables to the concrete to the pile to the sort of formwork, the erection, and the very, very clean little picture in that corner is the manufacturing of the bearings, which were, when we visited them for the testing, were on a sort of white linen table and had been sort of dismantled. So you go from these kind of almost 19th century spaces where people are hammering metals and sort of doing sort of absolutely nightmarish jobs up to a point, into these kind of sometimes very immaculate, delicate places where some more elaborate or more technologically complex items are being fabricated. So that's all the sort of things we play with. And in a way, when you look at projects from that angle, you may not necessarily recognize them. These 4 pictures are 4 extremely well-known architectural pieces of work. I'm going to show them to you in a second, but they are, in a way, that's possibly where we come in as engineers, is being able to transform some sort of image or idea into something that actually can be made. And there is no reason it has to be the engineers that is actually doing that task. There's absolutely no reason for that, except a sort of historical split between architects and engineers, and also maybe a curiosity for making things, which goes with being an engineer that is maybe slightly different from the one from architect. But I take real heart in seeing the presentations this morning and all the schools actually teaching about making and making things and making big models, prototypes. So I think there's something are also changing, and probably for the best in that respect. So these projects are, and I've chosen a few projects, where Toyoito Taichung, the Centre Pompidou Metz, the Serpentine Gallery, and the Chanel Pavilion, which are projects which are either all finished or in the case of Taichung, in the process of being built. I've chosen them because they all have geometry issue, they all have digital geometry and fabrication issues, and they also bridge the gap to the more analog aspects of the fabrication. Ultimately, it's still going to be people with hands and sort of tools making those things up to a point. I mean, there will be digital tools, there will be manual tools, but there's still a very analog part of making things in the construction industry. So just to go a bit more in detail, I've chosen 2 projects which are about I've chosen them for materials. And as I thought that actually steel was the one that had gone the furthest into developing the relationships, I chose the other 2 for the other 2 main materials of the structure world. So Taichung Opera House, this is the model of the main part of the structure. So this is actually structural part, and it's concrete. Shown on this size, you don't have any idea what I'm showing to you. It could be that big, or it could be that big, which is actually sometimes a problem of these digital tools, because they make it, everything's possible, and then suddenly you realize that when you cut it into manageable size, it's actually absolutely ginormous. But this is a relatively large building. And in a way, what has happened there is that we haven't just designed for making, we've actually learned by making and informed the design, which is relatively rare, actually. It's relatively rare that we're able to mock up parts of building, and in this case, actually increasingly large parts of the building, in order to develop the methodologies that will feed into the design. This is going to be built with sprayed concrete technology. It's something we've been using for other types of projects. We've used it in the UK for a couple of projects. The first one was the Birmingham by Future System, the Birmingham shopping centre, and that was just for a facade. Then we moved on with the Darwin Centre, where the actually egg shape inside the Darwin Centre is also a sprayed concrete structure, but this time it is part of the main structure. I think Taichung will be really way ahead of most of these in pushing that technology. So several mock-ups. I mean, you can see there's been, we started designing Taichung probably 4 or 5 years ago, and the mock-ups have followed on. We're at the 4th mock-up on this one. Same sort of questions that Wolf has raised. Issues of exchange of data, issues of rationalization, issues of parametric changes, how you deal with all this. What I'm showing you here is just a few images of how we generated the rebar geometry. Because the rebar geometry is actually what drives and what will govern the geometry of the whole piece. You create the rebars first, and then you pour the concrete. So you had to sort of decide how you do the rebar geometry. You could have basically sliced what is called the catenaries in, just sort of all different, non-parallel, sort of radial type of slices, and done your rebar cages for each of those. But I think it is still fair to say that despite the abilities of technology and despite the abilities of contractors and fabricators to fabricate more and more bespoke things, there is still a great deal to say for some amount of repetition in the fabrication process. And that's something most people don't really want to hear, especially in architecture schools, but I really believe that there is a need for some repetition in terms of economy of projects. There's still some of that. So what we did is we modeled the catenaries as a sort of more of there's some driving lines, basically, some parametric lines. And we decided to create the rebar cages in parallel sections for at least a good part of those catenaries, which is the ones that you see here. And then infilled in radial parts the corners in between those elements. So you had a mixture of very parallel elements and a mixture of radial. That, of course, ended up translated in a series of drawings for the rebar elements. And there I should add that we derived the geometric principle for that project, but we didn't do the whole exercise on every single catenary. Local Taiwanese company who is handling probably more like our friends who are the next speakers, produced the drawings for every single one of the elements. And that's the thing that happens, is that it creates a need for a large handling of data that can be done by, it could have been done by us, we could have done it, but in that instance it sort of worked best with a Taiwanese company coming into the picture. And then it ends up quite analog. This is the early mock-up, so I think they did it slightly differently later on, but that's the sort of early mock-ups. And then they sort of assemble the different elements, install them on site, put the sort of mesh that surrounds the cage and will hold the concrete in place, and you are left with this, which is the final mock-up, the more recent mock-up. And you might think, my God, this looks absolutely terrible. But I look at it and I think it's an absolutely fantastic achievement. The fact that it's mottled is irrelevant because there will be a finish. It's a sort of, the structure is not entirely visible, or at least its surface is not entirely visible, because actually its geometry is extremely pregnant into the building. But so you can sort of really learn, and we learn every step of the way. Every single one of these mock-ups fed back into the loop of the sort of tools which were used and the tools which were developed to generate the next bit of the design and into the analysis. So it was really having some preliminary idea, testing them with a mock-up, coming back to the design, and so on for at least 3 or 4 times for this project to sort of be able to happen. The project is currently on site, but the catenary in their full fabrication haven't yet started, but they will be quite soon. The rebars are being installed for the ground floor. Quite a different example is the Pompidou Metz. In a way, the technological abilities of the parties were quite different in the case of the Centre Pompidou. And it's quite interesting that the method of work of Shigeru Ban is by making, design models. He likes to make models. If you ask him to do anything digitally, it's going to be quite painful. He doesn't. That's not his style. At least that was not his style when we did this. He may have developed it since and maybe has changed his views, but his models, these fabricated models in the workshops, were generally more accurate than the drawings. If something was on the model, it was in the project, but it may not be on the drawings or on the thing. So he did a number of models of this mesh of the timber roof of Metz. But as you can see, all we got from him in terms of geometry was the chicken wire model that you have here. And in a way, I think I've been asked the question, would you have liked him to give you more geometry? And I think that's a really interesting debate, because to an extent, being able to do the geometry yourself means that you are able to make sure it is as smooth as it needs to be, as continuous as it needs to be, that it serves your purpose, as well as actually serving the architecture. So I'm actually not completely sure that actually giving the geometry or getting it entirely from the architect is necessarily the right thing. I think the exchange between the two is quite important. And then we developed the geometry, and we did it. I hope this is going to work. It might do. No, it's nice to do. Okay. I'll try it again. Sorry. Yeah. Well, almost doesn't matter. We'll look at it at the end. The form finding is a sort of engineering technique to create membrane structures, been developed a while back. It's not a geometry tool in any way, but at the time, the geometry tool was certainly less developed than they are now, and we used the form finding to generate the geometry of the mesh that is forming the roof. And we would send, we were asked by Shigeru to send him 2D elevations along the 6 main directions of the building for him to look at the geometry. And we would receive these sorts of instructions from him to move the model to the next level. As you can imagine, it took a little bit of time to actually get from a sketch like this to a finalized geometry with Shigeru. But I'm not. This is of course slightly amusing, but it's not a criticism in any way. It's actually a way that we work through this. And that's the way he was comfortable working with. I will pass on one slide over probably about 18 months of very, very complicated structural design on this project. But the thing I wanted to show you is that ultimately, in order to look at the results, we would almost reproject the results onto the shape so that we could understand how many of the elements were working. The little bits of red don't work yet on this image, and will require further looks and further special cases. So sometimes with these kind of large and complex geometry and large number of elements, you almost need to do it back visually to actually assess where you are in terms of your design. It's almost impossible to look at it in a table of results. Of course, making that one is a particular challenge. Every single piece is different. And I think one of the next speakers knows even more than I do about that. Every single one, so it's a complete opposite of what I said earlier. There's been no rationalization, no attempt at repetition. Every single element, even in the build-up of the sections, where there's 2 layers, are different because they're different, they're related to the main surface. It's twisted and turning in all directions, and it has to be made, and then brought to site and assembled. There was more or less 2 ways of making those pieces, and one of which has been shown to you by one of the previous speakers about lamination. You sort of create a form, and then you lay your laminates, and then you sort of clamp and glue and create a laminate which is actually shaped. Doing this at the scale of 100 by 100 meter roof with that many elements was completely impossible economically. It would have totally killed the project, which didn't have such a huge budget for something like this. And the other idea was that you would fabricate a piece of laminated timber, a normal one, sort of straight one, and then you would CNC the shapes inside that block. The problem with that is that timber, what is important in timber design is the grain. It's the grain of the wood. And by doing this, you're potentially cutting the grain of the wood across or putting it at an angle to the main flow of forces, which is a bad idea because you lose a lot of strength quite rapidly. So actually the job that will probably be described in a short moment by the next speaker was to find a way of optimizing the lengths of element and the way they were cut inside of the blocks such that the grain was never more than 3 or 5 degrees from the main direction of the plank. And that is quite a task mathematically, and that's where the team came in to actually do that piece of work. It was commissioned by the contractor to actually do this piece of work for them, which is this optimization. So not only all the elements were different geometries, but they were also different lengths, because as you can imagine, when basically the grain was becoming too far from the 5 degrees, you had to sort of crop the element and start again. So quite a bit of optimization of the pieces, but then you ended up with a very, very large number of spaghetti elements and with a referencing system that would have to be assembled on site. And ultimately, you end up with probably one of the most complex thing I've ever worked on, but an absolutely fantastic roof. So, but as you see, it was designed that the digital proportion of it was quite different from the different parties. And there is room for maneuver between these examples. So I think that's where we are more or less at the moment. We're doing these complex geometry, complex structures with these tools. I think the tools are changing all the time. Nobody had heard of Grasshopper even probably 2 years ago, or except some very sort of small confidential distribution. Now it's almost one of our day tools. It's moving all the time, this goalpost, and I think the relationships are changing. They are changing, and they are, at the moment, they enable a discussion at each project to have this discussion about who's doing what. And in a way, it's not a bad discussion to have. I don't think you'll decide to have always the same model for all the projects. I think you can choose between the models that Wolf has shown us, actually, for the different projects, and it will depend. It might be one for one part of the project and one for another part. But at least this discussion is now happening at various levels, and is really helping, I think, the process. We used to think that we knew what we were doing. Now we have to talk a bit more about who's doing what and how we're going to do things. That's it.
Thanks, Sophie, for your fantastic talk. I'd like to now introduce Fabian Schorer, who will probably, as Sophie said, pick up. Is he first? You sure?
I'm fine talking about
Okay, let's go with you. No harm. Fabian is the founding partner of Design to Production and leads the company's office in Zurich. After graduating from the Technical University of Munich with a degree in computer science and architecture, he worked as an assistant for the university's computer-aided architectural design group.